Okay, let's dive right in. The biggest story out of NeurIPS 2025 wasn't just one paper, it was a collision of worlds. For the first time ever, the premier AI conference hosted a dedicated workshop on wireless communications. Think about that. What happens when the world's top AI researchers finally focus their full attention on the wireless industry?
Right, so NeurIPS is the Super Bowl of AI. But why is this collision happening now? Hasn't AI been used in networking for years? What made 2025 the flashpoint where it suddenly deserved its own dedicated workshop, this AI for Next G thing?
Yes, and that's the perfect question. It's about a step change in complexity. We're moving beyond simple optimization. What came out of that Qualcomm-sponsored workshop isn't just academic. It directly impacts every major telecom strategy decision you'll make for the next 3 to 5 years. It's a whole new playbook.
A new playbook, I like that. But are we talking about a complete rewrite or just a few new trick plays? Because honestly, when I hear AI in telecom, my mind goes to slightly more efficient signal routing, not a fundamental revolution. Is this really that big of a deal?
Okay, let's kick off with the AI for Next G workshop. This wasn't just another session, it was the first ever NeurIPS workshop dedicated to wireless AI. Think about that. Their mission was to expose the core ML community to wireless challenges, and with 61 papers now public on open review, they didn't just knock on the door, they blew it clean off its hinges.
Hold on, 61 papers accepted from 72 submissions? My calculator says that's an 85% acceptance rate. For a top-tier conference like NeurIPS, doesn't that feel surprisingly high? Was this just a rubber stamp session?
Yes, and that's the genius of it. It wasn't about being an exclusive club, it was about throwing a massive open house. The organizers' explicit goal was outreach. How else do you get the AI community hooked on these domain-specific problems? You don't filter them out, you invite them in, show them the cool stuff, and get the conversation started.
So it was a bridge-building exercise, not a gatekeeping one. That makes sense, especially when you see the speaker list. You had industry giants like Qualcomm and Nokia sharing a stage with academics from MIT and Yale. It's like they were trying to create a unified field theory of wireless AI right there in one room.
Okay, let's talk workshop numbers, because the real story isn't just the 9.5 hours they spent in a room. It's who was in that room. We saw 5 industry leaders and 6 academics. That's nearly a 50-50 split at NeurIPS, which is wild. But here's the real question. What does that signal to the research community?
So what does it signal? A nearly even split sounds nice, but why is that the headline? Isn't this just the telecom industry trying to poach the best academic minds? This feels more like a talent grab than a deep research collaboration. Convince me I'm wrong.
Forget the papers for a second. The biggest signal at NeurIPS 2025 was a $1 billion signal. NVIDIA dropped a cool $1 billion on Nokia to turbocharge AI-native RAN. This isn't just a research grant, it's a statement. It says the 8-year research marathon is over and the commercial sprint has just begun. The clock is officially ticking on this tech hitting the real world.
Whoa, $1 billion is a lot of GPUs. But what is AI RAN, and why does it need to be at the radio edge? Isn't the cloud powerful enough? It sounds like putting a supercomputer on top of every cell tower, which seems excessive.
Yes, and that's exactly the point. Think of it like local reflexes versus thinking. Instead of sending data to the brain, the cloud, and waiting, the decision happens instantly at the antenna. As Dr. Alvaro Valcarce Real from Nokia Bell Labs said, they now know they'll have Blackwell-class compute right where it's needed. This is about making the network itself intelligent, not just a dumb pipe.
Okay, so it's about network intelligence. The AI RAN Alliance defines pillars like AI for RAN to improve the network, but also AI on RAN for new apps. So this isn't just about better 5G reception, is it? This is about turning the network itself into a platform for entirely new AI services.
Okay, let's start with the most staggering fact from NeurIPS 2025. Out of 9,825 accepted papers, guess how many were on wireless? 0. I'm not kidding. Julian Forge, Ericsson's principal AI researcher, said he walked the poster hall every single day and found nothing but papers on biological cells, not cell towers.
Hold on, 0 in the main conference? That feels impossible. So the entire wireless domain is just invisible to the world's top AI researchers? Why is that? And more importantly, why should our listeners care about this academic blind spot?
Yes, and that's the core of the wireless AI gap. It's a huge challenge, but also a massive opportunity. Think about it. The AI community is developing these incredibly powerful general-purpose tools, but they aren't being applied to some of the hardest problems in connectivity. It's like having a supercomputer and only using it to play solitaire.
So the industry is solving problems with one hand tied behind its back. But flipping that around, it means anyone who bridges that gap now gets a massive head start, right? They can build that competence before the AI native tech giants even realize wireless is a goldmine of interesting problems to solve.
All right, we've set the stage, and now for the main event. We've compressed a 9.5-hour fire hose of pure genius from that AI for Next G workshop into the 20 most critical findings. We're talking 61 papers from teams like Nokia and Samsung, all boiled down to pure insight. Ready to dive in?
Okay, hold on. 20 findings from 61 papers is a serious filter, so you're not just going to list them, right? How do you make sense of that? Are we talking foundation models, edge AI, semantic comms? Where do we even start with all that?
Yes, and that's the key. It's not a list, it's a map. Think of it like panning for gold. We sifted through hundreds of slides to find the nuggets and group them into themes. We're connecting the dots between, say, LLMs in the protocol stack and what Samsung is seeing in the field. It's about revealing the pattern.
Got it. So we get the findings, we see the patterns, but your agenda then jumps to paradigm shifts and decisions. Isn't that a huge leap? You're saying these technical papers actually force organizations to change course now?
Okay, the most mind-bending demo for me came from Nokia Bell Labs. They're using reinforcement learning for Layer 2 scheduling in 5G. The model has to decide who gets bandwidth in under 50 microseconds. That's not a typo. It's 20 times faster than the network's 1 millisecond heartbeat. How is that even possible?
50 microseconds? My brain can't even process that. Why does it have to be that quick? And how can any meaningful AI model even run in that time? It sounds like you'd need a supercomputer, not something at the edge of a cell network.
Yes, and that's the genius of it. As Dr. Valcarce Real explained, the model is tiny by design. It has just 13,000 parameters. He joked that's about the same number of neural synapses as an earthworm. It has to be that small and simple to run on edge hardware within that insane time budget and actually work in practice.
An earthworm-brained AI running our 5G? I love it. So the real breakthrough here isn't just speed, it's efficiency. This proves you can deploy specialized RL models in the most time-critical real-world systems imaginable. This is truly where the simulation meets the road.
Okay, so this diagram is crystal clear. You see the key numbers right on it. Just 13,000 parameters and latency under 50 microseconds. That is insanely efficient. But here's the real question. Is that the whole story? What the diagram doesn't show is the massive training investment, the simulation of radio physics, the reward function that defines good. That's the real competitive moat.
So you're saying anyone could copy this tiny model, but they couldn't get the same results. What makes that training environment so hard to replicate? Is that the moat? You can see the castle, the efficient architecture, but you can't cross the water to actually build it yourself because the physics simulation is so complex?
Okay, let's talk about a total paradigm shift. At the Nokia keynote, Valcarce Real laid it out. Designing a 5G scheduler used to take thousands of engineers years. Now, they can train a replacement with a team of 5 engineers in a single day. Can you even wrap your head around that leap in efficiency? It's staggering.
Whoa, hold on. 5 engineers replacing thousands? That sounds less like an improvement and more like a magic trick. How is that even possible? What is this new reinforcement learning approach actually doing that the traditional manual process isn't?
Yes, and it's about exploration. The old way is like trying to navigate a giant maze by hand, one turn at a time. You leave huge areas unexplored. As they said, we just don't know what we are missing. The RL approach systematically explores the entire policy space at once, finding optimal paths a human team would never even consider.
So the competitive moat isn't just a bigger model. The slides suggested the real secret is the quality of the training framework and their proprietary network data. It's less about having the biggest brain and more about having the best curriculum and the most unique textbooks to learn from.
Okay, this is the real kicker. Forget cost for a second. The diagram shows the traditional approach has unknown gaps, literal blind spots. It's like a chef who only knows 5 recipes. But what if the best dish isn't on their list? Reinforcement learning, by its very nature, is designed to explore the entire kitchen and find those amazing new recipes human engineers never even thought to write down.
So you're saying this isn't just about doing the same engineering job better, it's about discovering entirely new ways of doing it. The blind spots aren't just minor oversights, they're potentially huge opportunities we've been systematically missing because we were stuck in our old rule-based thinking. Is that the core takeaway for leadership?
Okay, the Deep Schedulers workshop was electric. The big question hanging in the air, which Samsung's Yang Lee voiced, was can we create an AlphaGo for wireless networks, a scheduler that learns through self-play to outperform anything a human could design? It's no longer sci-fi. It's being actively pursued right now to solve that massive sim-to-real transfer problem.
Whoa, an AlphaGo for networks? But how do you even start? You can't just let a brand new AI run a live cellular network. It would be chaos. The adaptive GNN-based proportional fair scheduling paper mentioned behavior cloning. What is that, and why does it matter for avoiding that chaos?
Yes, and that's the genius of it. Behavior cloning is like giving the AI a masterclass from the best human-designed schedulers first. Think of it as a student pilot in a simulator with an instructor. They learn the safe, proven moves before they ever try to fly solo. This accelerates learning and, crucially, avoids those risky early mistakes in a live system.
So you give it training wheels, basically. You teach it the current best practices so it has a safe starting point. But here's the real question. Once it's learned from us, can it then use that AlphaGo-style self-play to discover scheduling strategies that are fundamentally better than anything we ever taught it?
Okay, the big story isn't just AI and networks, it's where. We're seeing LLMs climb the protocol stack. As Nokia showed in their keynote, they've pushed AI to Layer 3, the Radio Resource Control, or RRC. This isn't just tweaking a signal, this is teaching AI to run the network's brain.
Hold on. The network's brain is a powerful image, but what does that mean in practice? What is this RRC layer actually deciding for me when I'm walking down the street with my phone?
Yes, and it's the master controller. The RRC decides which cell tower you connect to, when to hand you off, all that complex stuff. The Nokia team fine-tuned models like Llama on raw 5G protocol messages, so the AI learns not just the syntax, but the semantic intent behind the network's choices. It's replacing thousands of brittle, hand-coded rules with genuine understanding.
So it's learning the why behind the configuration. But aren't these models massive? How can they possibly run something that understands protocol semantics at the network edge? It seems like you'd need a supercomputer in every cell tower.
Okay, this heat map makes the ROI shift totally concrete. It's not abstract anymore. Look at the 3 distinct stages they've laid out. You have maturing tech at the bottom, active in the middle, and the frontier at the top. It's like a strategic map showing exactly where the R&D battles are being fought and where the territory has already been settled. How cool is that?
Yes, and seeing those stages is powerful. But are maturing and frontier just fancy labels, or is there a real punchline here? The source mentions a statement from Nokia right on the figure. So what's the direct implication? Why does knowing you're in the active zone change how you allocate your R&D budget tomorrow?
Okay, this is huge. We're talking about LLMs becoming network operators. The Tele-LLM Hub paper introduces Tele-MCP. Think of it as a universal translator, a bridge that lets an AI agent directly pilot the complex machinery of a telecom network. We're talking simulators, deployment tools, the whole O-RAN control loop. It's wild.
A universal translator for a network? I love that, but hold on. What's so special about this MCP bridge? Why can't the AI just connect to the tools directly? Is this just adding another layer of complexity for the sake of it?
Yes, and that's the magic. MCP is becoming the standard for connecting agents to any tool. As Ericsson's Julian Forchard said, this lets agents control telecom-specific tools directly. Without it, every connection is a custom, brittle job. With Tele-MCP, it's plug and play. The agent can now speak network fluently.
So it's a standardized plug, I get it, but what's the end game? Does this mean, as that LLM as a network operator paper proposes, a human could just say, make the network faster in downtown, and the AI actually configures the network to do it? Is that where this is headed?
Okay, the magic here is the MCP server. Think of it like a universal translator for every single telecom tool. Each tool gets this wrapper, which lets an LLM agent discover and use it instantly, no custom code needed. It's the connective tissue that finally makes intent-based network operations a reality your teams can build today.
A universal translator? I like that. But hold on, haven't we always had APIs and middleware? What makes this bridge layer so different? Is this just a fancy new name for integration, or is there a fundamental shift in how the agent understands and uses these tools without that brittle custom integration work?
Okay, next up is a critical warning for anyone deploying LLMs in telecom. The SafeCom paper found a shocking paradox. The more you fine-tune a model on telecom data to make it an expert, the more its original safety alignment degrades. You're essentially trading safety for specialization. How wild is that?
Whoa, hold on. That sounds like a huge problem. So if I teach my AI about network protocols, it might forget it's not supposed to generate harmful content? Why? Is it like the AI's brain only has so much room and the new knowledge pushes out the old safety rules?
Yes, and that's a perfect way to think about it. The fine-tuning process can overshadow the initial general safety training. But here's the fascinating flip side from the LACP paper. Instead of AI just learning from telecom, it proposes our industry's protocol expertise can serve as a blueprint for how AI agents should communicate with each other.
So, on one hand, telecom data can weaken AI safety, but on the other, telecom principles can make multi-agent AI systems more robust. It's not just about AI changing telecom, but our decades of experience shaping the future of AI. That's a much more empowering angle for the industry.
Okay, the biggest real-world shockwave came from Samsung's AI receiver. Forget simulations. As Yang Li presented, they put this on a live campus network with 64 antennas and got over a 30% throughput gain. This isn't a lab curiosity anymore. This is happening now.
Hold on, 30%? That's a massive leap over their own commercial-grade algorithms. How is that even possible? What is the AI doing that a traditional, heavily optimized system isn't? Where does that extra performance come from?
Yes, and that's the architectural genius. A normal receiver processes signals step by step. The AI model looks at everything: time, frequency, and all antenna signals simultaneously. It's like going from listening to one instrument at a time to hearing the entire orchestra at once to perfectly isolate the melody.
So it's not just faster, it's fundamentally more aware of the signal's context. And the biggest gains were in the noisiest, low SNR environments, right? That's where networks usually struggle. So this basically closes the book on the "does AI really work at the physical layer" question, doesn't it?
The Samsung field results chart tells such a clear story. Just focus on that low SNR column on the left. That's where the AI advantage is most pronounced. In good conditions, conventional algorithms are fine, but in those noisy, interference-heavy environments, that's where AI's ability to jointly denoise across dimensions really pays off, and the results are just staggering.
Okay, so break that down for me. Jointly denoise. Why is that the secret sauce? Is it like having smart noise-canceling headphones that can distinguish a whisper from wind from a car horn all at once? Why does that give AI such a massive edge specifically when the signal is weak and messy, but not when it's clean?
Okay, forget hypothetical AI for a second. The Samsung keynote showed two massive right-now wins. First, they're using AI to slash the chatter between your phone and the cell tower, the channel state information, or CSI, by a staggering 50 to 75%. This isn't a lab experiment. It's already being standardized in 3GPP Release 18. It's happening now.
Whoa, hold on. Slashing chatter by 75% sounds huge, but what does that actually mean for me holding my phone? Is my connection faster, or is this just about making the network more efficient for the carriers?
Yes, and that efficiency directly impacts you. Think of the network's bandwidth as a highway. CSI feedback is like every car constantly shouting its status. Samsung's AI compresses that shout into a tiny, efficient whisper. This frees up lanes, reducing congestion and allowing for more and faster data traffic for everyone on the network.
So it's about smarter resource management. That makes total sense. And speaking of smart resources, the keynote also mentioned a 15% energy saving by putting cell towers to sleep. Is that the same AI at work, just finding a different kind of efficiency?
Okay, the biggest surprise for me was channel estimation. 18 papers. The standout, robust channel representation, is all about creating models that work in the messy real world, not just a perfect lab. It's like they're finally training these AIs for the wilderness instead of a sterile zoo. The workshop chair even called this research foundational for the field.
Hold on, why is that so foundational? I get moving from the lab to the real world, but what does a robust representation actually do for my phone's signal? Why is it so hard to just take what works in the lab and deploy it?
Yes, and that's the core problem. A lab model is a finely tuned instrument for one specific song, but the real world is a chaotic jazz festival. This paper builds a representation that understands the music itself. And others are combining old and new. The physics-informed NN's paper blended signal physics with deep learning and got a massive 5 dB improvement in accuracy.
A 5 dB improvement is huge, no question. But here's the kicker. What if we're acing the wrong test? That no ground truth position paper really made me think. It challenges the entire premise, asking if our benchmarks even measure what matters for a production network. Are we just getting better at a game that doesn't reflect reality?
The single most ambitious vision came from Ohio State's GLU. He asked, what if we stopped building dozens of separate AI models for wireless tasks? Instead, why not build one foundation model, a GPT for wireless, that learns the fundamental physics of the channel itself and then specialize it for everything else?
Okay, a GPT for wireless is a catchy headline, but why is that actually better? Don't you lose performance by not having specialized models for, say, traffic analysis versus something like beam prediction?
Yes, and that's the billion-dollar question. The bet is that a shared foundation is more efficient. As the Neurosymbolic Wireless Foundations Models paper shows, you can add constraints for reliability. It's like teaching a doctor all of human anatomy first, then letting them specialize in cardiology or neurology.
That anatomy analogy really clicks. So what's the honest framing here? The wireless community today feels like natural language processing did back in 2017, right? Lots of task-specific models, but no dominant foundation. We're waiting for that consolidation moment.
Okay, the big story out of NeurIPS has to be the hub and spoke model for foundation models. Imagine one giant pre-trained brain, the hub, that understands the fundamental physics of a problem. Then, for each specialized task, you just fine-tune a little spoke off of it. The economics are just staggering. Pre-train once, then cheaply fine-tune for dozens of different applications.
Yes, and that model is super intuitive, but why is it a game changer now? What's the real difference between this and just training smaller, specialized models from scratch like we used to? Is the cost and time savings of fine-tuning from a shared foundation truly that massive compared to the old way?
Okay, one of the most revealing moments was from Ericsson's Julien Forget, who basically admitted to having Tesla envy. He showed Tesla's model, all sensors in, steering and acceleration out, and asked, what if we could do that for Telecom, a single, elegant Telecom foundation model? It was such a bold, honest moment.
Hold on, Tesla envy? A mobile network is a beast of standards, regulations, and hardware from a dozen vendors. It's not a self-contained car. How could you possibly package that into a single piece? It sounds like a fantasy.
Yes, and that's the key. He said they're nowhere near it today because of that exact complexity. But it's not a literal blueprint, it's an aspirational North Star. It's about defining the grand challenge. Can we unify this sprawling, heterogeneous system? That vision is now driving the R&D roadmap for the next 3 to 5 years.
So the goal isn't to build a telecom car, it's to escape the complexity trap that's holding the industry back. The envy is for the simplicity of the vision. This is the strategic horizon they're all aiming for, even if it feels miles away today. Got it.
Okay, the Best Paper Award was a showstopper. The winner, Optimal Neural Compressors, finally gives us the perfect map for navigating the eternal triangle of communication: speed, accuracy, and the new magic ingredient, human perception. Think of it like a sound engineer's mixing board for data. We used to only have 2 sliders. This paper just gave us the third, crucial one, and the manual to master it.
Hold on, why is perception a separate slider from accuracy? I always assumed if a signal was mathematically perfect, it would also look perfect to us. What's the difference?
Yes, and that's the revolutionary insight. An image can be pixel-perfect accurate, but feel sterile or uncanny. This work makes perceptual quality a first-class goal. It's the theoretical foundation for semantic communications, designing systems around what a human needs to understand, not just what a machine decodes. We're talking about the architectural blueprint for 6G.
A blueprint for 6G is huge, I get that. But here's the real question. Is this just beautiful math on a whiteboard? Or did the researchers give us something engineers can actually build? Is it practical for, say, a device on the edge?
So picture this. For decades, sending data was like making a perfect photocopy. You only cared about rate versus distortion. But the semantic comms triangle asks a radical question. What if the goal isn't a perfect copy, but a perfect understanding? It adds a third vertex for what the application actually needs to do. Suddenly, it's not a line, it's a whole new surface to explore.
Hold on, a surface? So you're saying we might intentionally send a less than perfect copy? Why would we ever do that? Isn't the whole point of communication to get the information across with 0 errors? What does what the application needs even mean in practice?
Okay, this next one is huge. For 75 years, all digital communication has followed one rule from Claude Shannon: compress your data, then encode it for the noisy channel. 2 separate jobs. But what if we could smash those steps together? That's Joint Source Channel Coding, or JSCC, and it's not just an update, it's a revolution in how we send information.
Hold on, so you're saying every single piece of wireless tech I own uses that 2-step process? Why did we ever separate them in the first place? And what does it mean for an AI to do both jointly? Is it just doing the same things but faster?
Yes, and that separation was a brilliant simplification. But JSCC is a game changer. Think of it like a translator and a radio operator working together instead of in different rooms. The AI learns to create a message that's already resilient to static. As Qualcomm's Dr. Taesong Yu said, this challenges the very foundation of our physical layer design.
So it's not just a new codec, it's a whole new architecture. But what's the real impact? Is this the kind of thing that could actually reshape the design of future 6G networks? Or is it a cool but niche idea? We're talking about a potential architectural replacement for the modem in my next phone, right?
Okay, this is wild. Imagine instead of sending a photo of a cat pixel by pixel, you just send the idea of fluffy cat on a red couch. That's what the Beyond Prompts paper on diffusion-based semantic communication is doing. They're using the same AI that generates images to radically compress and transmit meaning itself. It's like telepathy for machines.
Hold on. Telepathy for machines? I love it. But why does that matter? Is it just about saving bandwidth, or is there a bigger picture here? If my phone sends the idea of a cat, how do I know I'm getting my specific cat and not some generic internet cat?
Yes, and that's the crucial question. It's about efficiency, but more importantly, it's for machine-to-machine talk. The VLF-MSC paper showed this perfectly. An autonomous car doesn't need a beautiful photo of a stop sign. It just needs the feature stop sign ahead. It cuts out the middleman, the human eye, and co-designs the communication directly for the AI.
So we're building a native language for AIs to talk to each other? And I saw another paper mentioned, the MOE semantic comms one, that gets rid of channel feedback. Is that part of the same efficiency push, making the conversation not just smarter, but also less chatty and resource-intensive?
The biggest shocker for me was Edge AI. We think of AI as these giant cloud brains, right? But the scatterplot showed that Telco Edge AI is operating 3 orders of magnitude faster and smaller. It's like comparing a Formula One car to a cruise ship. They're both vehicles, but built for totally different worlds. This isn't just scaled-down cloud AI. It's a whole new sport.
A whole new sport? That's a bold claim. So you can't just take a 70 billion parameter model and put it on a diet? Why is it a fundamentally different engineering discipline? What breaks when you try to just shrink things down for the edge?
Yes, and that's the crux of it. You can't just put it on a diet because you lose crucial flavor. The magic is in new techniques, like what the data-free quantization of neural receivers paper showed. They're getting models to work with 4-bit precision. That's like speaking a language with way fewer words with almost no performance drop. It's a total rethink of model architecture.
Okay, so this new language is more efficient, but what's the payoff? The Pearl paper tested Llama 3 on devices for radio adaptation. What does that actually mean for us? Does my phone get smarter at finding a signal in a crowded stadium because of this?
Okay, this latency graph is wild. The log scale is key. Each line is a 10x jump. The Nokia Deep Scheduler and a cloud chatbot aren't just different points. They're in different universes. It's like comparing a race car's reaction time to a cargo ship's turning radius. This proves Edge AI isn't just small AI, it's a whole different discipline, right?
Yes, and that's the crucial insight. So you can't just take a massive cloud model and put it on a diet to run on the edge. It's a fundamentally different engineering problem. So what specific expertise does this different discipline demand that a cloud-native data scientist might be missing? What's the secret sauce for the edge?
So the biggest story for Telco coming out of NeurIPS is how the small model ecosystem is finally ready for prime time. Our Topic 20 analysis found serving a 7B model is 10 to 30 times cheaper than a Frontier 70B model. Think about that. We're not talking about a small discount. We're talking about a fundamental shift in the economics of Edge AI.
Cheaper is one thing, Iapetus, but what about speed? Is it just a cheaper, slower version? Because for real-time applications on the edge, latency is king. Are these small language models actually hitting the performance targets we need on a device you and I carry around every day?
Yes, and that's the kicker. They are fast enough. The Liquid AI team demonstrated their LFM2 models hitting 21 to 32 millisecond response times on a standard Samsung Galaxy S24. That's already approaching that critical sub-50 millisecond range. It's like we've gone from needing a supercomputer to getting near-instant answers from a pocket calculator.
Okay, so the models themselves are fast, but I'm thinking about the poor engineers. Isn't deploying to a dozen different types of constrained hardware a total nightmare? It's one thing to have a great model. It's another to actually get it into the wild without a 6-month engineering project for every single device. That's the real bottleneck, right?
Okay, this next theme is huge, making AI work at the network edge, where bandwidth is gold. How do you get powerful AI insights without clogging the pipes? The few features are enough paper had a brilliant answer. O-RAN controllers can be incredibly effective with dramatically less data. It's a total game changer for efficiency.
Wait, hold on. Using less data to make smart decisions sounds like a paradox. How can you be sure you're not throwing out the most important signal with the noise? Why is saving that front haul bandwidth so critical?
Yes, and that's the genius of it. It's like a master chef knowing they only need salt, pepper, and garlic, not the entire spice rack. You save trips to the pantry. The conformal sparsification paper takes this further, using uncertainty to decide when the edge really needs to phone a friend in the cloud. It's selective intelligence.
So it's a two-pronged attack. Be picky about the data you send, and be picky about when you ask for help. But is this just a clever patch for current systems, or does this, as the Adaptive Lightweight AI Transceivers paper suggests, point to a whole new way of building networks from the ground up?
Okay, this is brilliant. Federated learning is a natural fit for telecom. You have millions of devices, all with sensitive data. But here's the real question. How do you train a model when the updates are sent over noisy, real-world wireless channels? The Federated Learning over Physical Channels paper proved that even with all that static and signal corruption, the training still works.
Hold on. So you're saying the phone call between the device and the central server can be fuzzy and full of static, and it doesn't break the entire learning process? How is that even possible? Does it just mean training takes forever, or is there some trick to clean up the garbled messages?
Yes, exactly. It's like learning a recipe from 1,000 chefs all whispering ingredients over a bad connection. The system is just robust enough to handle it. And what's more, the MARFL paper then showed how to make those whispers more efficient, reducing the coordination chatter. So it's not just possible, it's becoming practical for massive real-world networks.
Practical is great, but you mentioned sensitive data. If these updates are flying through the air, what stops a clever attacker from piecing them together? The block mod shift paper talks about protection, but how do we really know my data isn't being reverse engineered from these gradients? That seems like the real hurdle for any serious enterprise or government use.
Okay, let's talk emerging tech. One paper that blew my mind was on 6G security. They're using a statistical tool, Granger causality, to act as a network watchdog. And get this, it achieves 89.2% accuracy in spotting attacks in under 100 milliseconds. That's faster than you can blink. How's that for a rapid response team?
Wow, that is fast. But why is that speed the critical piece? I get that high accuracy is important, but in a massive network, what does a fraction of a second really buy you? Isn't just catching the attack the main goal?
Yes, and it's because 6G networks are like apartment buildings with shared utilities. The authors of that paper showed this speed lets you pinpoint the exact tenant causing trouble before the fire spreads to other network slices. It's not just detection, it's immediate surgical attribution.
Ah, so it's about preventing collateral damage in real time. That makes sense. But all that high-speed processing sounds incredibly energy-intensive. Which brings me to that neuromorphic radio paper. Are they trying to solve similar problems with a fraction of the power, using brain-inspired chips?
So when you pull back from the individual papers, what's the real story? It's not 5 random projects, it's 5 puzzle pieces clicking into place, proving the AI native network isn't some distant vision, It's being built, layer by layer, right now.
Layer by layer sounds slow. Are these just isolated lab experiments, or is this stuff actually getting close to production? And who is doing the building? Is it the usual suspects?
Yes, and that's the kicker. It's the vendors on your short list. Nokia proved RL-based scheduling works in real time with a tiny model. Samsung deployed AI receivers on their actual Korea campus and saw meaningful gains. This has moved from concept car to the first engines rolling off the assembly line.
Okay, so the radio layer is getting smarter, but a network is more than just radios. What about the rest? Are we seeing that same assembly line progress with things like automation, or what's happening at the edge?
Okay, the biggest paradigm shift at NeurIPS this year was a tectonic one. As Nokia's Valkaris Rial put it, the low-hanging fruit of AI in the physical layer has been plucked. The entire research frontier is moving up the stack to layers 2 and 3. It's not about just the signal anymore, it's about the whole system.
Hold on, does that mean all the amazing physical layer AI we've seen is suddenly obsolete? I mean, we know Samsung is getting huge field gains there. Are we just supposed to abandon that work?
Yes, and that's the crucial point. It's not about abandonment, it's about marginal returns. Think of it like gold mining. The easy surface gold is gone. You can still dig deeper for more, but the real mother lode, the highest ROI, is now in a new mountain. Our analysis showed Layer 3 research at a 92% ROI. That's the new frontier.
A new mountain! I love that. So what does mining that new mountain even look like? What were the standout papers at these higher layers, like Nokia's LLM RRC, that prove this is where the action is?
So this protocol ROI heat map is basically a treasure map for researchers. You see that big cluster of 18 papers at Layer 1? That's the well-trodden path, lots of activity. But the map directs our attention to the frontier at Layer 3 and the 3 papers at Layer 2. It's screaming, the real treasure, the highest return opportunities are over here.
Okay, that's a powerful visual. But hold on, why is a crowded field a bad thing? Isn't more research activity at Layer 1 a sign of a healthy, important area? Why should we divert incremental investment away from where everyone is already working?
Okay, so the big takeaway for every R&D leader listening is this paradigm shift. Don't abandon your physical layer AI work. Those CSI compression gains are real. But the urgent message from NeurIPS is to build capability in layers 2 and 3. Scheduling, network management. That's where the highest ROI window is wide open right now.
A wide open window? That sounds almost too good to be true. Why the urgency? If the physical layer work is delivering concrete results, why pivot so hard? Are we just chasing the next shiny object?
Yes, and it's because that window won't be open forever. The AI native companies haven't really discovered the juicy problems in wireless protocols yet. This is our chance to get a head start. The XAI on RAN paper even gives us the explainability tools to deploy this stuff in mission-critical systems, bridging that gap.
So it's a land grab before the broader AI community arrives on the scene. For a manager, does this mean reallocating headcount? Moving people from Phi AI to Protocol AI? That feels like a massive, potentially risky internal shift.
Okay, get this. The biggest paradigm shift is moving from handcrafted rules to learned policies. Imagine thousands of engineers spending decades writing network rules. Now, reinforcement learning lets a team of 5 tackle a scenario in a single day with a universal framework. We saw this with AlphaFold, and now wireless scheduling is the next domino to fall.
Whoa, hold on. 5 engineers replacing thousands? That sounds almost unbelievable. So the old competitive advantage, that massive investment in human expertise, just evaporates? Why is a learned policy better than rules tested against known scenarios for years?
Yes, and the advantage doesn't evaporate, it moves. The new moat isn't engineering headcount anymore. It's your training pipelines and your proprietary network data. It's like shifting from handcrafting one perfect key to building a master locksmith machine that can learn to pick any lock. The value is in the learning system itself.
Ah, so it's the same pattern we saw with Google's ML-based chip placement. The secret sauce becomes the data and the framework, not the handwritten instructions. Is this already happening? Are teams like the ones behind the adaptive GNN scheduling paper actually deploying this?
Okay, look at the unknown gaps row in this figure. It's the whole story. Traditional heuristics can only cover scenarios engineers already anticipated. It's like having a map for only the known roads. But what about the wilderness? RL's systematic exploration finds solutions in corners that expert rules never even knew existed. This isn't just a performance boost, it's a totally different way to build intelligence.
So you're saying the old expert rules were a carefully curated travel guide, but RL is like an all-terrain vehicle exploring the entire landscape? Why is that so critical? Weren't the known roads good enough for most network traffic? I mean, how often do we really go off-roading in a data center?
Okay, beyond new skills, the most profound shift is how these systems fail. We're moving from predictable, deterministic bugs to what Juniper's Bob Friday calls non-deterministic agentic AI. He said the entire software QA process has to change. Think about that. How do you verify something that isn't supposed to do the same thing every time?
Wait, that sounds chaotic. You're saying we're trading a bug we can write a clear test for a ghost in the machine? Why is that a good trade? It sounds like we're just losing control over our own systems.
Yes, and it's less a ghost and more a creative chef. Old systems were vending machines, predictable but dumb. An AI agent is a chef. You can't write a unit test for make a tasty snack. You have to design its reward function, its sense of taste. That's the new core engineering skill.
A chef who might give me a beet salad when I wanted chips. So if you can't test it traditionally, how do you trust it? How do you even know why it chose beets? Is that where explainability work, like we saw in the XAI on RAN paper, becomes absolutely critical for debugging these policies?
Okay, Paradigm Shift 3 is a total game changer. We're not just bolting AI onto networks anymore like in 5G. We're talking about 6G as an AI native system. Imagine a network that isn't just a pipe for data, but a unified, self-organizing system where AI is a first-class architectural citizen. It's a fundamental rebuild from the ground up.
Hold on, first-class citizen sounds impressive, but what does that actually mean? For years, the story has been, let's use AI to optimize the network. What's so different now? Why is this a paradigm shift and not just a better version of the same idea?
Yes, and that's the brilliant reversal. As Cambridge's Mihaela van der Schaar put it, the relationship is flipping. She argued that the wireless community's decades of experience in distributed, multi-agent systems is exactly what frontier AI research needs now. It's not just AI helping networks, it's network design driving the cutting edge of AI.
So it's a two-way street now? That's wild. The network experts are becoming AI pioneers. But is this just a cool academic idea, or is there real-world commitment? Is anyone actually investing in this vision of a cognitive network?
Okay, so the keynote laid out this brilliant three-act play for the future of networks. You've got 4G, where we are now, 5G Advanced, the near-term evolution, and then the main event, 6G, as a fully AI-native system. But here's the kicker. All those amazing projects, the Deep Scheduler, the LLM RRC, they're the literal building blocks for that 6G column. It's a blueprint, not just a dream.
I get the timeline, but why frame it that way? Is this just telling operators where to invest, or is there a deeper technical reason for separating 5G Advanced from a truly AI-native 6G? What makes that final column so fundamentally different that it needs its own category, instead of just being better 5G?
So the biggest news is that the 6G journey has officially begun. Qualcomm's Dr. Taesong Yu confirmed it. 3GPP Release 20 is the starting gun. And the core idea isn't just faster speeds, it's making the network AI native. But here's the real question. What does that actually look like in practice?
Okay, hold on. AI native gets thrown around a lot. Are we just talking about bolting some AI features onto the existing infrastructure, or is this a complete teardown and rebuild? Why does this distinction even matter?
Yes, and it's a total rebuild from the ground up. Think of it less like a bolt-on and more like a nervous system for the network. The AI RAN Alliance provides the governance, the brain, if you will, and then you have things like Nokia's Deep Scheduler that let the network optimize and even heal itself without human intervention.
A self-healing network. So you're saying every single one of these incremental advances, these rungs on the ladder we've been talking about, is essential to close that wireless AI gap? Without them, this whole vision of a fully autonomous 6G network just remains science fiction?
Okay, the NeurIPS 2025 floor was buzzing about agentic AI meeting wireless. This isn't just theory, it's happening now. Imagine, self-organizing AI agents are becoming self-healing network cells. Your phone's connection could literally fix itself before you even notice a problem. How cool is that?
That is cool, but is this just the AI world dropping its latest tech into the wireless industry's lap? Or is there a real two-way conversation? I mean, are the telecom experts just taking notes, or are they contributing back to the fundamental AI research?
Yes, and that's the paradigm shift. It's absolutely a two-way street. The wireless community is contributing crucial architectural patterns. The LACP paper, for instance, inverts the whole thing. It proposes that wireless protocol layering should inform how AI agents communicate. The teacher is becoming the student.
So the AI field is looking at established telecom architecture for inspiration on how to build better multi-agent systems? That's fascinating. It's not just AI for networks, but networks teaching AI. That must be the core idea behind that building the cognitive network paper everyone was talking about.
Okay, get this. The biggest paradigm shift isn't just about making models bigger, it's about making them right-sized. We're talking a 7-order of magnitude spectrum. On one end, you have Nokia's 13,000 parameter Deep Scheduler, making decisions in under 50 microseconds. It's a scalpel, not a sledgehammer.
Wait, hold on. 13,000? In a world of billion-parameter giants, that sounds like a pocket calculator. Why would you ever go that small? Is it bigger always better?
Yes, and that's the genius. For real-time scheduling, you need insane speed, not Shakespeare. You need a race car, not a freight train. That's why on a Samsung S24, a mid-size model can do radio adaptation in milliseconds, while a 7 billion parameter model handles slower network strategy. It's all about matching the tool to the task.
So the big insight isn't just small models are back, it's efficiency is king. This connects directly to the scaling efficiency analysis we saw in Topic 17, right? Where things like CDP pruner are getting massive latency reductions for models at the network edge.
Okay, so NeurIPS didn't just give us theory. They laid out a literal 3-horizon roadmap for AI and wireless, and the first horizon, just 6 to 12 months out, is already kicking off. We're talking AI RAN schedulers accelerated by NVIDIA's Blackwell investment and new specs in 3GPP Release 18. It's not a what if, it's a what's next.
Hold on, you listed a bunch of things for that near-term horizon. Schedulers, safety gates like SafeLoRa, monitoring pilots. What's the common thread? Are these just a collection of cool projects, or is there a bigger strategy at play in this first phase?
Yes, and that's the critical insight. The strategy is safety first. Before you let an AI drive the network, you install guardrails. That's why the LLM monitors are advisory only, and why SafeLoRa and Safe Merge gates are being implemented before any LLM touches the control plane. It's about building a secure foundation.
So we're building the foundation, but the long-term vision is an AI-native 6G with self-organizing agents? That feels like a massive leap from just installing safety sensors. How do we get from a carefully monitored pilot to a network that basically runs itself? What's the bridge from Horizon 1 to Horizon 3?
Okay, let's talk roadmap, because this isn't just a wish list, it's a battle plan. The near-term green section is all sequenced by readiness based on hard workshop evidence. First up, deep schedulers. Why? Because the approach is proven and the hardware is already committed. It's the lowest-hanging, juiciest fruit on the tree.
Hold on. Sequenced by readiness? So this isn't just a random to-do list. They're saying the order itself is the strategy? Why does starting with schedulers and not, say, safety gates give them the best shot at success right out of the gate? What makes that the domino that has to fall first?
Okay, so after all the mind-bending theory at NeurIPS, what can teams actually build right now? The big one is deep schedulers. Nokia's RL-based scheduler is basically production-ready. And get this, the models are tiny, just 13,000 parameters. You can run these on today's edge GPUs. It's the lowest-hanging, highest-impact fruit on the tree.
A 13K parameter model is definitely not a behemoth. But why start there? The slide mentions 4 high-impact actions. What makes the scheduler so special compared to, say, LLM monitoring or that MCP thing?
Yes, and that's the key. It's about maturity. The scheduler is like a finished recipe ready for the kitchen. The LLM pilots, like the RAG for radio regulations approach, are still in the tasting phase, advisory only, no network control. And MCP is foundational plumbing. You need the plumbing, but the scheduler is the shiny new faucet you can turn on today.
That makes sense. So, what about CSI compression? The slide says specs are final, but it flags a weird constraint: vendors not sharing models and using sequential training. That sounds complicated. Why can't they just share the AI models to make it work?
Okay, so this priority matrix is fascinating because it's a trick question. Everything lands in the high-impact zone. The real question isn't what to do, but how you sequence it. You start with low-effort wins like CSI compression and LLM pilots to build organizational momentum and prove the value fast.
Wait, so if they're all high impact, why not just jump to the biggest prize? Why bother with the low effort stuff if deep schedulers are the ones that deliver the highest sustained advantage?
Okay, the single most critical strategic framework from the entire session was this build versus buy matrix. Forget the tech for a second. This is a roadmap for survival. It answers the billion-dollar question: where do you spend your precious R&D, and where do you just swipe the credit card?
Hold on. A 2x2 matrix is a classic consultant slide. Why is this one so critical? What's the secret sauce in that build quadrant that you can't just buy off the shelf from NVIDIA or Meta?
Yes, and that's the genius of it. The build quadrant isn't about making a better base model. It's about creating the factory, the unique RL training frameworks and simulation environments for your proprietary network data. This is where Nokia's Team of 5 advantage lives. The moat isn't the model, it's the data and infrastructure that feeds it.
So you're saying everyone's fighting over the celebrity chefs, but the real win is owning the farm and the kitchen? Then, for the buy quadrant, is it really that simple? Just grab some Blackwell GPUs and open source models? It feels risky to treat those as commodities when they're evolving so fast.
The most arresting thing from NeurIPS this year was seeing safety alignment just plummet. The SafeCom paper showed it visually. You take a smart, safe LLM, fine-tune it on telecom data, and it's like its safety programming just evaporates. The model dives right into what they call the danger zone. It gets great at telecom, but forgets how to be safe.
Hold on, why is that so much scarier than a chatbot giving a weird answer? I get that it's not ideal, but what's the real-world harm? Are we talking about a network that suddenly develops a dark sense of humor?
Yes, and that's the multi-billion-dollar question. It's not about humor, it's about control. This isn't a chatbot, it's a co-pilot for the entire network. A misaligned model could misconfigure thousands of cells, knock out service to first responders, or leak sensitive network data. The stakes are astronomically higher.
So it's like handing the nuclear codes to a brilliant but unstable intern. The SafeCom work mentioned defenses, right? Things like SafeMerge. Is this just a recommendation, or is it more like don't even think about deploying without this?
Okay, this next risk factor is huge, the sim-to-real gap. As Professor Anand Sarwat from Rutgers put it, what you can do in simulation is very different than actually using radios. We're seeing brilliant models trained in these pristine digital worlds that just completely fall apart when they hit the messy, chaotic real world. It's a massive problem.
Hold on, why is real so different? I thought the point of a simulation was to model reality. What are these perfect simulations missing that causes these amazing AI models to underperform so badly in the field?
Yes, and they're missing the chaos. It's like the difference between a flight simulator and flying through a real hurricane. The simulation can't capture all the random RF interference, the hardware nonlinearities, or sudden traffic bursts. It's why Samsung's 30% plus gains were so amazing. They made field validation a core discipline, not just a final checkbox.
So what's the takeaway then? If you're not a giant company with your own campus to test on, are you just stuck building models that only work on paper? How can a regular research team even begin to de-risk this?
Okay, here's the billion-dollar question for 6G. How do you get two AIs to cooperate when their creators are fierce competitors? Your phone and the cell tower need to sync up, but neither side wants to reveal its secret sauce. This is the interoperability problem, and with 3GPP Release 19 concluding in 2025, the clock is ticking to solve it.
Wait, that sounds like a classic tech problem. Why is this different? Can't they just define a standard interface, like an API, and let the models talk through that? Why is it so hard that we're calling it a major risk factor?
Yes, and that's the crux of it. As Qualcomm's Dr. Yu put it, how do you train these autoencoder models to work together without knowing the other's design? It's like trying to invent a secret language with someone, but you're only allowed to pass notes through a government censor. You can't just talk freely to figure it out.
Okay, that analogy clicks. But they have a workaround, right? You mentioned sequential training. So if there's a temporary fix, why is this a race? What's the real strategic play here for companies getting involved in the 3GPP working groups right now?
Okay, let's talk urgency. The 3GPP timeline is like a series of gates slamming shut. Release 18 is done. That ship has sailed. But here's the real question. Are you on the boat for Release 19? Because that's your window to influence things before the big one. Release 20 defines the entire 6G AI native architecture. The window is closing.
Whoa, so it's not just a suggestion, it's a deadline with huge consequences. If a company's standards team isn't in those Release 19 and 20 working groups right now, are you saying they're essentially locked out of defining the future? They'll just have to live with whatever everyone else decides for 6G?
Okay, this next one is a bombshell for anyone in software. Bob Friday from Juniper Networks basically said their entire QA process had to be thrown out for agentic AI. Why? Because it's not deterministic. You can't just ask if it passed. You have to ask a human expert, did we actually make it better? Imagine that.
Whoa, hold on. So my trusty green checkmark from a unit test is gone? What does that even look like in practice? You just line up network engineers and ask for a thumbs up? How do you scale that without it becoming totally subjective?
Yes, and it's less like a pass-fail and more like a panel of judges at the Olympics. They use domain expert scoring panels, sophisticated A/B testing, and staged rollouts. It's a whole new paradigm. The XAI on RAN paper even explores the deep trade-offs here between transparency and speed in these critical systems.
A panel of judges. I love that analogy. But it also sounds incredibly expensive and slow. Is the big takeaway here that companies need to budget for a whole new, very human-centric verification department from day one, or their AI projects are doomed?
Okay, let's land the plane. The single biggest takeaway for any telco listening is this: the time to act is now. Not next year, not next quarter. The research is clear. The ROI window for AI in layers 2 and 3 is open today. But as Paradigm Shift 1 showed, it's already starting to narrow. This isn't a wait-and-see moment.
Okay, hold on. The window is narrowing sounds dramatic. Why the sudden urgency? Are we saying if you don't jump in right now, you're permanently left behind? What's the actual tangible risk of waiting just 6 more months?
Yes, and it's because the rules of the game are being written as we speak. The 3GPP AI ML standards in releases 19 and 20 will define the competitive landscape for a decade. Waiting is like showing up to a high-stakes poker game after the cards have already been dealt. You have to be at the table now to influence the rules.
So it's about both building and influencing. Got it. But moving fast sounds risky. The Safecom paper showed real degradation curves, right? How do you move fast and implement these LLM safety gates without, breaking the entire network?
All right, let's look ahead to 2026. My highest confidence bet, we're going to see the first commercial AI-RAN deep scheduler deployments by major operators. We're talking real, live networks using powerful Blackwell-class GPUs targeting the first half of the year. This is happening, folks.
Okay, that's a bold claim, but AI ran deep scheduler sounds incredibly technical. Why should anyone outside of a network engineering department care? What does that actually do for my phone?
Yes, and it's the key question. Think of it like a hyper-aware air traffic controller for your data. Instead of just following a fixed rulebook, it predicts congestion and optimizes your signal path in real time. Given Nokia's demonstrated timeline and NVIDIA's investment, it's a near certainty for a smoother, faster connection.
The air traffic controller makes sense. But what about the LLM prediction? It says pilots will be in an advisory-only role. That sounds like we're letting the AI watch the network, but not actually touch the controls. Why the caution?
So, not all predictions are created equal, right? The scorecard splits them into high and medium confidence. High confidence is for stuff where investments are already made and specs are locked. It's like the foundation is poured. Medium confidence? That depends on multiple, separate research groups all hitting their targets. It's much more of a gamble.
Okay, so it's the difference between a sure thing and a parlay bet. But why make that distinction so explicit? For someone planning their company's roadmap, how should they treat this? Are the medium confidence items just wishful thinking we should ignore?
Okay, if you're a builder, this is the slide you screenshot. It's the ultimate what-to-watch list. You've got everything from the super practical, like the LLM hub for deployable models, to the foundational theory in the optimal neural compressors paper. This is the toolkit for the future, right here.
A toolkit is great, but it's a long list. It feels like drinking from a fire hose. If I'm a developer trying to build something safe and responsible, which one of these is my absolute first read? Where do I even start?
Yes, and that's the perfect question. For safety, you immediately grab the SafeCom paper. It's becoming the essential reference for every deployment team. But see the pattern? It's not just a list, it's a full-stack recipe, a theoretical foundation, a safety guide, a deployment tool. It's all here.
A recipe. I like that. But how much of this is just brilliant theory versus stuff we'll actually see in production? What makes something like Nokia's Deep Scheduler different? What's the secret sauce that gets it out of the lab and into the real world?
Okay, so we've talked theory, but how do we know any of this AI for wireless actually works in the real world? That's the magic of the Cosmos testbed. It's not a simulation, it's a live city-scale environment in New York City where researchers can field test their AI. They have an actual instrumented intersection in Harlem for urban mobility scenarios.
Wait, a real intersection? Why is that so important? Can't you get the same results from a super advanced computer model? What's the big risk of just staying in the lab?
Yes, and that's the key. It's all about closing that sim-to-real risk. Think of it like this. A flight simulator is fantastic, but you don't really know how your plane handles unexpected turbulence until it's actually in the air. Cosmos is that real airspace for wireless AI. It's the most direct path to proving your AI native RAN approach is robust.
Got it. So it's the ultimate proving ground. But that sounds incredibly complex. How does a smaller team even get started? Is there a movement to make this amazing infrastructure more accessible so it's not just for a few elite labs?
Okay, the biggest mic drop from NeurIPS 2025 wasn't a paper, it was a lack of papers. Ericsson's Fergiat found exactly 0 wireless posters in the main hall. 0! It's like throwing a huge party for the future of tech, and the entire telecom industry isn't on the guest list. What does that even mean for the field?
Whoa, 0? But wait, does that really matter? I mean, they have their own conferences, right? Is this just about academic bragging rights? Or is there a real danger in the wireless world being siloed away from the core AI community like that?
Yes, and it's a huge danger. It's the wireless AI gap in action. Imagine you're building the world's best engine, but you're not in the same garage as the people designing the chassis. Your engine never gets into the race car. It means R&D leaders are making investment decisions without the competitive pressure that drives real innovation.
So it's less about a trophy and more about being left out of the fundamental design process for the next decade. The real question then, the one 4G had posed, is what does the wireless community need to do differently to crash that party and earn a spot in the main conference hall by NeurIPS 2027?
Okay, let's dive into the absolute treasure trove from the AI for Next G workshop. We're talking 61 papers, and this is just the first slice. The big themes are clear. Network optimization, channel estimation. It's like the entire future of wireless communication is being prototyped right here on Open Review. The sheer variety is stunning, from GNNs for scheduling to federated learning.
Whoa, hold on. You just dropped federated multi-agent reinforcement learning like it's a casual Tuesday. What does that even mean for my phone's connection? Are a bunch of tiny AI agents fighting over my bandwidth? And why is this such a big deal in network optimization?
Yes, and that's the perfect way to think about it. Imagine instead of one central tower dictating everything, you have a team of local AIs learning together to manage traffic, but without sharing everyone's private data. It's cooperative intelligence for networks. It's about making the system smarter from the edges in, a huge theme at the workshop.
Okay, a team of local AIs. I love that. That makes sense. So beyond that, what about channel estimation? The list mentioned a ground truth at a position paper. That sounds less like a research paper and more like a philosophical debate. What's the story there?
Okay, the sheer variety in this next batch of papers is wild. We're talking everything from ultra-efficient edge AI with papers like Pearl, all the way to designing waveforms for satellites with autoencoders. But the real showstopper? The semantic communications track, which actually snagged the Best Paper Award this year.
Hold on, semantic communications sounds like something out of a sci-fi novel. What does that actually mean? Are we talking AI that understands the meaning of the data it's sending, not just the raw ones and zeros?
Exactly, yes. And think of it like this. Instead of sending a huge photo of a cat, which is tons of data, it sends the concept, fluffy orange cat on a blue chair. The diffusion and vision language papers are showing how to do this. It's about transmitting meaning, not just pixels. It's a total game changer.
So it's about being smarter, not just faster. And that must tie directly into the other areas, right? If you're sending less data, that's a huge win for federated learning, where privacy and communication efficiency are everything, or for those lightweight transceivers they mentioned in the Edge AI section.
So, the final slice of the workshop pie is huge. Network management was the star with 12 papers. Think about that. We're not just using AI on the network anymore. Papers like LLM as operator are showing how AI is becoming the network operator. It's like the AI is now the air traffic controller for our data.
Hold on, LLM as operator? That sounds incredibly ambitious. Is this just a theoretical model, or are we talking about an AI literally configuring routers and managing traffic flow by itself? What's the real-world impact of handing over the keys like that?
Yes, and it's not just a one-off. The cognitive network and deep RL scheduler papers are all building this same future. The real insight is moving from static, rule-based management to a dynamic system that learns and anticipates. It's less if-then and more what-if for the entire network stack.
So the AI is becoming the brain, but does that brain understand the physics? I see another category, physical layer and RF, with wild stuff like GSRF, 3D Gaussian splatting. How does this high-level operator AI connect to the nitty-gritty of how radio waves actually travel through a building?